Got it. Well, welcome to the February program meeting. We have a great program tonight. We've got Dr. Dennis Conti from the AAVSO, and who is a friend of SDAA, and a lot of us have taken his courses and worked with him. It's on the wacky world of exoplanets and how we discover them. If you look at our calendar, you notice a couple of things. In addition to us being very busy with outreach activities, we are beginning to go back to the schools again, which is very, very nice. I don't know what the weather's going to be like for the next 3 days or so, but we have a school tomorrow, a park in West Sycamore. I think the forecast is bad for West Sycamore. The Agua Caliente County Park is a 2-day event. Dennis, do you want to say anything about that?
Yeah, the 17th is canceled because of weather.
Okay, so it's just the 18th.
No, and then I'm going to be there on the 19th. So if you want to sleep over on the 18th and the 19th of February, I'm going to be doing a constellation talk out there. You can bring your scopes and support me. So the 17th is pits for weather. So 18 is a Saturday night and 19 is a Sunday night. And then the next day, Monday, is President's Day weekend, or President's Day. So their park is all full on that Sunday night also.
Okay, that sounds good. Thanks for the update.
It's on the calendar also.
Well, I pulled it yesterday, so that's anyway. I don't know about TDS. The weather doesn't look terribly good for TDS this weekend either. Notice that we're going back to the Borrego Springs Library in February. Again, and close out February with KQ Ranch. Without talking to everything, note that on the 8th of March, we have Lake Dixon. This is for SDAA members. So if you call with the contact on the calendar, who is a ranger and an SDAA member, she can arrange for you to come and set up. And it's a good opportunity to do telescope testing, your own observations, check out your camera system in case it hasn't been operating during all this bad weather. The program meeting in the 15th of March will be live at Mission Trails. The speaker will not be live. She's from JPL, but we will have a live meeting. We're going to Coronado at the 23rd of March, the latter part. Can anybody talk to the Coronado Library?
Yeah, that's me.
Okay.
It's not at the Coronado Library is sponsoring a stargazing event, but it's at Coronado Cays. If you look at the calendar, it'll say the address for Coronado Cays, which is below the amphibious base.
Okay.
It's on the Silver Strand.
Always do some astronomy news. If you're into numbers of moons, Jupiter now has 92 moons, which surpasses Saturn for the record. People always ask us about moons. They're the latest numbers. And by the way, they are finding new high redshift quasars from this dark sky spectrographic instrument at the 4-meter telescope in Kitt Peak. And this interesting logo is from them, the Dark Energy Spectroscopic Upside Down Instrument. And also in a little bit of news from James Webb, they have, and as a segue into our talk tonight, the James Webb has confirmed its first exoplanet from a test candidate, which has a catalog number of LHS 475 Bravo. And I got the impression that they carefully picked one and then went out and verified it, kind of so they could say we did it. I always like to show an ASIC picture. I don't know when Hero actually took this. They're confusing dates on the on the ASIG site, but I'm going with the latest one they've published, which is 31 December. But you can never have too many pictures of the horse head. But if you look at the specs for this, he did it from TDS, but he used two different cameras. He used a ASI 1600, a color camera for a set of data, and then he used a monochrome camera just for the luminance shots, and he pulled it all together in PixInsight and toned it up in Photoshop. But you know, he really did a pretty nice job. And you know, if you've ever tried to do this, getting the colors right, getting the extent of the of this little kind of a wave-like front, and then handling the nebulosity and the one bright star Alnitak, it's kind of hard to do this well, and I think he did a super job of it. So maybe that'll be the ASIC challenge for next month. Anyway, let me introduce our speaker. He's Dr. Dennis Conti. He's a retired telecommunications professional and an amateur astronomer. He does have a PhD in computer science from Purdue, and he founded the AAVSO Exoplanet Section and has continued as a section leader ever since then. He's an author of A Practical Guide to Exoplanet Observing, and he has helped AAVSO members obtain certification with NASA to work with the test satellite data on exoplanets, including a number of SDAA members. And I don't know, Mike, if you're in the meeting, but I've taken Dr. Conti's course. I think Scott did. Mike Chasen. I think my son was there. You know, we've all enjoyed all this information, and it's very encouraging to think that we could actually do something important and contribute to science. So with that, let me turn the meeting over to Dennis Conti. And would you like us to hold our questions to the end, or would you rather handle them as they come?
Yeah, if you could, if everyone could hold their questions to the end, I think that should work fine.
Okay, that's good. So at this point, please give a big SDAA welcome to Dennis Conti, and then mute your microphone, please.
Okay, can you see that okay, Ken?
Yes.
Okay, good. Well, good evening, everybody. Thank you for giving me the opportunity to speak with you on my favorite subject. As you see the title, The Wacky World of Exoplanets and How We Discovered Them, what I'll be covering is the different types of exoplanets, different orientations, and in particular, how we, and by we, I mean those of us on this call, amateur astronomers, how we discover them and how we help the professionals to confirm the existence of exoplanets. What you see on the cover slide here, in fact, is exoplanet LTT 1445A, small b. This is an exoplanet orbiting very close to its host star, and that system orbiting two other stars. So here we have an exoplanet. If you were to stand on the surface of this exoplanet, you would actually be seeing three suns. So one of many different strange orientations that we have now discovered in the world of exoplanets. Let me start with the big picture. We sometimes get caught up with a lot of the data analysis we're doing and forget what NASA's overall missions are all about, which is very simply to see if there's planets outside our solar system that support some kind of life. We're not talking about ETs, you know, we're talking about even microbial life. To answer that question, however, there's a number of other questions that exoplanet scientists first have to answer about a candidate exoplanet. The first is the planet rocky? The planet exoplanet could be gaseous, could be an ice giant, but we're hopefully interested in those planets that are rocky and that also support liquid water on their surface. We also interested in understanding the atmosphere of exoplanets, in particular biosignatures that would be meaningful to us in terms of elements that suggest there's some type of biological life. One of the questions that are facing exoplanet scientists these days is that they're now finding that whereas they had thought they had a small set of biosignatures that gave them high probability that there was life, they're now finding that some of those signatures might be caused by geophysical processes. So folks are not even quite sure now with 100% accuracy what are the elements in the atmosphere that kind of nail the question whether there's some type of life. So this in and of itself is sort of an ongoing branch of exoplanet science. So to study exoplanets helps us to answer these questions. As we go through the presentation, hopefully you'll see that we're actually down to the fourth question in terms of being able to start answering some of these important questions about whether exoplanets that we're looking at support life. And I'll be going into that in a little bit more detail. Now, one of the things I think a lot of folks may not realize is that over close to 90% of the stars that you see with your naked eye looking up at the sky have one or more planets orbiting them. Obviously, we can't see them from our perspective, even if we had a very large telescope because of the contrast difference between the host star and an exoplanet. But some of those planets are orbiting in an orientation from our point of view that are passing in front of their host star. We call those transiting exoplanets. Exoplanets, as we'll see in a minute, come in all sizes, from Earth size to many times the size of Jupiter. In fact, if we look at the whole different set of exoplanets, some of the ones that were discovered first, mostly because they were easier to discover, are so-called hot Jupiters. Obviously, the name signifies the fact that they are large, that is to say, of Jupiter size, and they're hot because they're very close to their host star, and therefore the period of their orbit is on the order of a few days. We know that there are systems that have multiple planets. The most famous one, and the one that's getting a lot of attention with James Webb, is the TRAPPIST-1 system, which has at least 7 planets orbiting its host star, and a majority of those planets are within the so-called habitable zone. That is to say, where they support liquid water on their surface. As you saw on the beginning slide, we have some planets that orbit their star in a multiple star system. We have some planets that we are now finding are free floating, and these planets could have been stripped away from their solar system for various reasons. But indeed, we are finding even free floating planets. We are finding planets that are orbiting in the opposite direction from the rotation of their star. As we'll see later, as far as the formation of planets, exoplanets, generally they would be orbiting in the same direction as the spin of the star, because they would have come from the same circumstellar disk that formed the host star, and therefore have been a product of the same angular momentum. But indeed, there are some planets orbiting in the opposite direction. This could have been because they were captured from another solar system. Maybe they were a free-floating planet that entered a particular system and then were captured by a star. And finally, we have planets that are disintegrating around their host star. And in fact, we have been able to detect, even us amateur astronomers have been able to detect such disintegrating planets. So as you see, many different orbital orientations, many different sizes, but the point here is that what we're finding in the world of exoplanets is much different from our own solar system. So to understand how exoplanets are formed, it's first important to know, to understand how their host stars are formed. If you recall, when James Webb was first, took its first pictures, one of the amazing pictures was the one you see here, which was a star-forming region of gas and dust, which was where stars are being formed. And if you look at the process of star formation, where this cloud of gas and dust then causes clumps to be formed, those clumps then generate dense cores, and the dense cores then form young stars from dusty disks around them. If you imagine an ice skater with their arms extended, and as they pull their arms in, they increase their rotation faster and faster. The same is true for a young star being formed. And furthermore, to use another analogy, if you take pizza dough and throw it up in the air, it sort of flattens out. And similarly, a star being formed will cause this circumstellar disk of gas and dust to be spread out. And it's from that circumstellar disk that planets are formed. So the process of planet formation is directly related to the formation of its host star. And it obviously comes from the same gas and dust cloud material that the host star was formed from. And I think I covered most of these points. The fifth point is basically saying that where a planet forms may determine its material. It could be a gas giant, such as Jupiter. It could be formed into an ice giant, such as Uranus, or it could form as a rocky planet, such as Earth. The composition of the planet is related to its density. And one of the things we're going to see in a minute is that one of the reasons for doing the exoplanet analysis that we are doing, in fact, is to help us determine the density of a planet and therefore what material it constitutes that exoplanet. And finally, the last bullet suggests that a young planet itself may have its own disk from which what we call exomoons may form. So how are exoplanets discovered? The most common method is the transit method. This is, again, going back to what I said earlier, where a planet passes in front of its host star from our point of view. It causes a dip in light of the star, and this tells us something about the size of the planet. It's been compared to a firefly flying in front of a lighthouse and be able to detect a very, very small drop in light of that lighthouse. This is similar to what a transiting exoplanet would cause the light of its host star to dip a very, very small amount. The transit method helps us to determine one of the two important factors in knowing the density of the planet. And that of course, is the size of the planet. But to get the density of the planet, we also need to know its mass. And this is where the radial velocity method comes into play. So the radial velocity method is basically relies on the movement to and fro from our point of view of the host star as the planet is orbiting it, it causes the star to move to us and from us. And we are able to detect that very small movement by looking at using spectroscopy, being able to look at the shift in wavelength, very much like the shift in wavelength of a train whistle coming towards us or away from us. So with that very small difference in wavelength, we're able to determine the radial velocity movement of the star, and from that, the mass. So with the transit method giving us the size and the radial velocity method giving us the mass, we're able to get the bulk density, which helps us answer one of those very first questions I posed earlier, which is the planet rocky? And finally, there are a couple of other methods, which if we have time later, I'll be happy to go into, that also help us to discover exoplanets, microlensing and astrometry in particular. Okay, so what I like to do is focus on the transit method, since this is the dominant method used by us amateur astronomers and professionals. And in the little animation you see here with a planet going around its host star, if we are measuring the flux of the host star, what we'll see is this characteristic bucket-shaped curve, where each of those individual gray dots represent an observation. The green dots represent a averaging of those gray dots, and the dark green line that generates the curve going through it is a transit model of what that exoplanet looks like. This, in fact, is an observation I made from my own backyard telescope here in suburban Annapolis, Maryland. And the point here is that even with modest-sized telescopes and regular amateur astronomer gear that you would use for deep sky imaging, we're able to detect these very small drop in light of a planet orbiting its host star. Typically, it should be pretty common to be able to detect a 1% drop in light, which represents about a 10 parts per thousand flux depth. It is possible in some cases to detect even half of that. So some amateurs are able to detect, based on their seeing conditions, 5 parts per thousand, or basically 0.5% drop in light. So the transit method is what we amateurs use, and has been one of the dominant methods so far for detecting exoplanets. Now, if I kind of zoom out that light curve, the point here is that there are many different things that we get just from the shape of the light curve, the duration of the light curve, and the depth of the light curve. We're able to determine, as I said earlier, the radius, that is to say the size of the planet. We're able to determine the size of the orbit, and we're able to determine the inclination of the orbit from our point of view, just by observing and modeling the transit curve going through our observational data. Now, let me turn to the NASA's current exoplanet discovery mission, TESS, Transiting Exoplanet Survey Satellite. The reason I'm doing this is because this is a prime example where amateur astronomers have contributed greatly to exoplanet discoveries, and in fact are continuing to do that. TESS is a space telescope that was launched in 2018. It has 4 cameras, and for 27 days, those 4 cameras dwell on a particular sector of the sky, and then the telescope moves to another sector. So after it has completed its survey of both the northern and southern celestial sphere, each of those sectors have been observed at least for 27 days. which means that by observing and dwelling on each sector, if there's an exoplanet transit that occurs twice, then TESS will identify that as a possible candidate. Now, you'll notice that there are some areas, especially at the poles, where there are overlapping sectors. And this is where TESS is able to help detect planets that have orbital periods longer than 13 days, which would be half of the 27 days. In fact, in some cases, 365 days. So TESS, being an all-sky survey, has to have certain limitations, which we'll talk about in a minute. As I said, TESS was launched in 2018 to conduct an all-sky survey. TESS focuses on nearby stars that are bright. And by nearby, we mean here 330 to 300 light years, whereas Kepler was dwelling on only a very small part of the sky in the constellation Cygnus. TESS is doing, as I said, an all-sky survey. One of the primary missions of TESS is to help find Earth and super-Earth-sized planets for JWST so the JWST can characterize their atmospheres. If you remember from some of those original questions where we said, is the planet rocky? Does it have an atmosphere? And what are the biosignatures in the atmosphere? This is what James Webb is helping us to determine now, is for confirmed exoplanets, what are the constituent parts of the exoplanet's atmosphere? As of today, TESS has identified over 6,000 planet candidates, and of those has confirmed so far 291. Now you might say, well, there's a large number of planet candidates, but only 291 confirmed. And the reason for this is because of the very rigorous process that the TESS science team goes through to change the status of an exoplanet from candidate to confirmed. And I'm going to be covering that in a minute. And in fact, this is where amateur astronomers play a huge role in helping to move a candidate from that status to confirmed. So in fact, if we look at the process of how that happens, once TESS has identified a candidate, that is to say, in its field of view, it has identified the fact that a target star has a characteristic drop in light, in fact, 2 drops in light, so we have some idea of the period. That candidate then is passed along to a ground-based follow-up team, where on the ground, for reasons I'll cover in a minute, it's necessary to further confirm that that drop in light is coming from a target star and not from some other, for example, nearby eclipsing binary whose light might be blended with the target and therefore causing a false positive. So one of the main purposes of the ground-based team is to relook at those candidates and to discern whether or not the drop in light is coming from a target star and in fact has the characteristics of an exoplanet, or if in fact what TESS was seeing was a false positive. And I'm going to be covering why that might be true in a minute. If the ground-based follow-up team, which consists of both amateur and professional astronomers, pass a candidate through that gate, then that candidate goes into high-resolution imaging to look further into the nearby neighborhood of the star to make sure there's no neighbor that might be causing this false positive. If it passes through that gate, then there's a more detailed analysis of the star itself to help refine its stellar parameters. And the reason for that is because we can only understand some characteristics of the exoplanet if we really understand the star itself. And that's why this reconnaissance spectroscopy is done, to really refine our understanding of the host star. And finally, radial velocity studies are done using Doppler spectroscopy to get the mass. So you can see that there's this rigorous process that a candidate that TESS has identified has to go through to pop out at the bottom, in fact, whether the planet is a confirmed exoplanet, or if in fact it was a false alarm or a false positive. So why do we need ground-based observers if we have this magnificent space telescope? Well, as I said earlier, because TESS has the potential for blending together in its image multiple stars where the dip in light could be caused by a true exoplanet or a false positive, we need ground-based observers to sort this out. Now, how is it that multiple stars can be blended together? Well, in order to do an all-sky survey, TESS has to have a very large pixel. So let's take a look, in fact, at a ground-based image. This, in fact, was an image I took from, again, my backyard telescope. And if you focus on the two stars in the middle, and we zoom in on those two stars, what you see here in the little checkered boxes are pixels from my camera. So each of those little pixels is, in fact, a pixel from my ground-based telescope. TESS, because it is doing an all-sky survey, has a very, very large pixel. In fact, to show you the relative difference, this is the size of TESS's pixel. So whereas my image scale, for example, might be 1 arcsecond per pixel, TESS's is 21 arcseconds. So whereas on the ground, we're able to separate out these two stars, TESS blends them together in 1 pixel. So TESS is not able to independently confirm where, in fact, that drop in light might be coming from. Is it from the star in the upper left or the star in the lower right? Furthermore, if we kind of zoom back out, where you see again the TESS pixel covering those two stars, it gets even worse. Because those of you familiar with differential photometry, where we apply a aperture over a area around our area of interest to determine what the flux is in that aperture, TESS's aperture is quite large. In fact, TESS's aperture covering a few pixels results in even a greater confusion as to where a flux depth might be occurring from. So for these reasons, we have to do ground-based observing, where we use our finer resolution telescopes on the ground to help to discern whether a false positive is happening or not. One of the most common scenarios of a false positive is if I have a target star on the left, which I'm hoping to determine if there's an exoplanet transit. If it has a nearby neighbor of an eclipsing binary, TESS blending those two together, that eclipsing binary would, with the combined light, would in fact, the combined light would mimic an exoplanet. On Earth, we're able to differentiate the target star on the left from the eclipsing binary on the right and make an independent assessment as to where that transit is occurring. It might be possible, however, that nearby eclipsing binary is so close to the host star that even our ground-based telescopes are not able to separate them out. In that case, we have to rely on large professional telescopes to determine, in fact, if there is a false positive occurring. We have the case where there's a host star that is orbiting a nearby eclipsing binary. So we have two transits taking place here. The eclipsing binary transit occurring and the host star itself transiting around a nearby eclipsing binary. So again, we have to distinguish where the dip in light is occurring. We have a case where the target star itself is an eclipsing binary, perhaps close to another nearby neighbor where blended together, it mimics an exoplanet transit. We have the case where there's just an eclipsing binary itself with a small secondary star that again might mimic an exoplanet transit. And we have the case where a star is grazing another star and that could mimic an exoplanet transit. So it is all these false positive scenarios that amateur astronomers are helping the professional community to determine whether in fact it's an exoplanet that is causing the drop in light or whether it's some other false positive condition. Now, we are able to detect these false positives in a number of different ways. One way is just looking at the shape of the curve. A bucket-shaped curve is generally characteristic of an exoplanet transit, whereas a V-shaped curve is an eclipsing binary. Alternating odd-even V-shaped curves are clearly a eclipsing binary. Alternating depths based on different wavelengths, in particular of blue versus red, will be indicative of an eclipsing binary. And even the depth of the curve, if the curve is beyond a certain range, the rule of thumb is if the transiting body is greater than 2.5 Jupiter radii, then it's not a transiting exoplanet. Now, to give you one practical example, we're trying to determine whether what we were seeing was an eclipsing binary or a transiting exoplanet. So an amateur astronomer colleague of mine captured this light curve in the with a red filter and got a certain depth. 11 periods later, that is to say an odd and even odd number later, I collected data with a blue band. When we superimpose them, you see that there's a difference. So the fact that it's both a V-shaped curve and a distinct difference when two different filters were used nailed the fact that this is a eclipsing binary and not a exoplanet transit. Now, to give you an example of what we on the test team have to consider, if you look at this picture here, the stars that have green labels, namely T labels, are within a 2.5 arc-minute radius of the target star. The ones that are labeled green are within a radius and of a certain magnitude, such that tests could potentially blend their light together with the target star, and that light of an eclipsing binary, if that's what one of those T stars are, could mimic an exoplanet transit. So from the ground, what we had to do was to test each of those stars to confirm whether or not they were eclipsing binaries. This was done originally by the team, taking hours to do. And in fact, myself and others, were able to come up with some software that streamlined the process that allowed them to make this determination in the order of minutes. So not only were we amateur astronomers able to help with the observations, but also to help with streamline the process for discerning whether in fact an exoplanet was truly causing the dip in light or whether it was an eclipsing binary. So to summarize our contributions, it turns out the majority of test follow-up submissions, the last time I checked, were being made by amateur astronomers. As I said, we've developed some tools and even developed the guidelines for the entire test team. And we are on the last point, we're actually helping with the analysis of observations from remote professional observatories, such as the LCO observatories that are in different geographic locations around the world. Now, looking ahead to future NASA missions, right now, Webb, of course, is looking at exoplanets that TESS has confirmed, looking at them in the near infrared to help characterize their atmospheres. The Roman Space Telescope, set to launch, last date I saw was 2026, will, for the first time, do direct imaging of exoplanets to help really get higher resolution as to the constituent parts of their atmospheres. So we're starting to now answer those earlier questions I posed to help us to get a better handle on whether in fact there is some form of life occurring on these exoplanets. So to summarize, I think it's fair to say we've greatly contributed to confirmation of exoplanets. Those of us who have gotten into exoplanet observing have primarily come from astroimaging, either planetary or deep sky imaging. And as I said at the outset, much of the same equipment and techniques that we used in astroimaging have applied directly to exoplanet observing. There's difference in software analysis and modeling, but even that software is readily available. And also, those of us who have contributed to TESS have the opportunity certainly to participate in real exoplanet science. And in fact, if our contributions are part of a discovery paper, we're named as co-authors of that paper. Right now, I'm personally, I think, co-author of probably close to 40 exoplanet papers. And finally, the AAVSO offers the training and software and tools to help anyone who is interested to enhance your exoplanet observing skills. As Ken mentioned, several members of your club, in fact, have gone through these courses. Now, to say a few words about the AAVSO, which stands for American Association of Variable Star Observers, we have, we're an international organization. In fact, I think the oldest organization of amateur astronomers devoted to advancing the science of astronomy. We do that through pro-am collaborations such as with TESS. We archive our data in long-term databases. We have a journal that is a referee journal of publications. We have just about all the tools and training you need to do science grade observations. And we have an annual meeting where we interact in person. We just had one, for example, in Tucson in November. And the heart of the AAVSO are our sections. What you see here, in fact, are the 12 sections that cover just about every part of astronomy science, from eclipsing binaries to exoplanets to long period variables, solar, and so on. My interest, of course, is the exoplanet section. I started that about 6 years ago. And its primary focus these days has been on TESS, but also it is supporting other missions as well. We offer courses. I'm conducting a course, began a couple of weeks ago and will go for the next 4 weeks. There's a guide for those of you who are interested. It's free on my website called A Practical Guide to Exoplanet Observing, which covers the best practices in exoplanet observing, and also is a step-by-step guide to using one of the more popular pieces of software called AstroMSJ for doing exoplanet analysis. We also have a qualification program for our members who are interested in participating on the TESS science team. And so far, we've qualified 26 members. So in conclusion, just as a thank you for allowing me to speak, we're offering a reduced membership rate for the first year for those of you who are interested in becoming an AVSO member of $40. This compared to the $95 normal registration fee. And if you are interested, just shoot an email to Lindsay Ward at lward@avso.org and just put your name and astronomy club in the email. And if any of you want to shoot me an email about other things of interest, feel free to do so at dennis@astrodennis.com. And my website has a number of different types of information. Again, that's where the link of the practical guide is. I also have some observation images and also calibration files that match the guide in its walkthrough of using Astro Image J. So you can actually get some real data and actually work through it with the guide, going from calibration all the way through to exoplanet modeling. So with that, let me stop, and Ken, if there's any questions anybody has, I'll be happy to entertain them.
I noticed that TESS uses ecliptic coordinates. From your diagram, the TESS's equator was the ecliptic, and
Yes.
north and south are the ecliptic poles.
Yeah, right.
You know, I can see a reason for that if we were talking about our own solar system, but if we're talking about the wider all sky, is there a particular reason for it, or are they just the way it happened to be?
Well, I think because it was trying to stay away from the ecliptic, so it was the orientation was just around celestial sphere as you saw it. So now I should have mentioned that there have been a number of extended test missions that are actually mapping the ecliptic plane as well, or stars in the ecliptic plane. But the first iteration was to stay away from the ecliptic plane. Are there any questions anyone has?
Any more questions?
Excuse me, I have a question. Actually, first, thank you very much for a nice presentation. But from your presentation, you show like there will be a variation that we can image for. I think but I just wonder how long can we observe such a variation? What's the time scale?
Right. So an exoplanet transit, typically for hot Jupiters, which is mostly the type of transits that we amateur astronomers are observing, would be about a 4-hour observation of the beginning of the transit to the end of the transit. But because we require a baseline before and after, then the total time could be 5 to 6 hours of an observation. And that light curve that you saw, in fact, represented about 5 hours.
Well, then that is very interesting, because I always wonder, just like if there's an alien looking at the actually imaging solar system for exo imaging, probably they won't be able to find Earth, right?
Well, first of all, in fact, there's been analysis done, believe it or not, as to the possibility of an alien on, I think it was, I forget what, one of the nearby stars, whether they could in fact detect us, Earth. And the conclusion, I think, was that the shallow depth that Earth transiting our sun would make would be pretty difficult. Not impossible, but would be pretty difficult. So there in fact have been actually simulations to try to tried to determine that.
Right. From what you say, I mean, I just wonder, does it require like the exoplanet transit before or after the actual star in a very short time, just like you say in 4 hours? Or, you know, if there's exoplanet actually circles around the star in a long time, like, can we still detect it?
Well, in fact, it would take, for example, to detect an Earth exoplanet would take 365 days.
Right.
To detect one transit, but to confirm the period, it would take twice that because you would need 2 transits to determine the period. So in fact, it would take what, over 700 days to determine the period of Earth if a alien was trying to discover us.
Very interesting.
Other?
Yeah, thank you.
Yep, sure. Any other questions?
You mentioned one of the methods of detecting exoplanets was astrometry.
Right.
Is that how you find these wandering exoplanets that are not orbiting their own sun?
No, I think you're talking about the free floating exoplanets.
Free floating, yes.
Yeah. Other techniques such as microlensing would be used there, where if looking at, I mean, using, you know, the same principles of bending of light that gravitational lensing is used for large, you know, galaxies that are lensing background galaxies that you've probably seen with Hubble or James Webb. The same principle applies where microlensing, if we're looking toward the center of our Milky Way galaxy, if a free-floating planet passes in front of one of those background stars and lenses the light of that background star, that's how we're able to indirectly detect that there in fact was a free-floating planet. The other approach is if the free-floating planet is a young planet and therefore very warm or hot, then using infrared or near infrared, be able to detect it that way. So those would be 2 ways to detect a free-floating planet. Any other questions?
We have one question from our audience, questioning whether or not the same principles could be used with radio telescopes to find exoplanets.
That I'm not sure. I mean, yeah, I don't know. I don't know the answer to that, quite frankly. If a radio telescope is able to detect a change in what frequency or something, if a exoplanet is transiting in front of a star, possibly, I guess. I honestly can't answer that.
Okay. A question from Philip Bianco, general AAVSO astroimaging question. Are you folks seeing streaks from starlight and OneWeb satellites in your images?
Oh yeah, I am. Yeah.
And I can confirm that we've seen them in Tarot.
Yeah,
absolutely.
Yeah, definitely. Yeah. I see that Jake has his hand up. Jake, did you have a question?
Yes, I was wondering, since most of the identifications of exoplanets are when they're transiting, can they be identified when they're not transiting, but when they're behind the star at a 45-degree angle, such that they would be reflecting the light backwards from the sun towards the Earth? Could they be identified by current technology?
Yes, with some. In fact, I think James Webb might be able to detect the light coming from a star as the reflected light off the planet from the star if it's hot enough. I believe that's true. That would be when it's doing what's called a secondary eclipse, when it's going in back of the star, I think is what you're referring to.
Yeah, I was referring to whether, in fact, if it was off of the star at a distance, whether you could actually directly measure the spectroscopy of the atmosphere, because the planet would be displaced away from the disk of the sun, but would be reflecting light from behind it towards Earth.
Yes, yes. In fact, one of the things that the Roman Space Telescope is going to do is to be able to do that directly, is to measure the atmosphere of those planets that in fact are distant enough from their host star. It's going to be using a coronagraph to try to black out the light of the star to be able to look at more detail the exoplanet atmosphere. Gary, I see you have your hand up.
Yeah. Hi, Dennis. Thanks for the
Hi.
talk.
Sure.
You mentioned there's 4 cameras on tests. You also mentioned the pixel size is pretty large. I didn't actually realize it was quite that large. Does that mean to say that for most stars that you're looking at within tests, there's some degree of contamination from a nearby star?
Yes. I mean, most is sort of a relative term, but a lot, yes. And that's why we need to do ground-based observing on every candidate, just to make sure that there in fact is no contamination causing or mimicking an exoplanet.
And the 4 cameras, are they similar or do they have different responses?
No, I believe they're similar. All right, I believe they're identical. Yeah.
Okay. All right. Okay. Yeah. Yeah. The reason I ask is because we've been doing quite a lot of flare monitoring, and the amount of data that you can see within a test download over 27 days is pretty incredible. I mean, you can see some really small flares, but I didn't realize there was this potential for contamination.
Yeah, I would think with also, because of the large pixel size, even with flares, trying to discern where it's coming from could be problematic.
Yeah, because I mean, you know, as you know, right, 21 arc seconds, that's
It's pretty
half
big.
of my field of view, right? So
Yeah.
I mean, there's a lot of stars in that generally.
Yeah.
Okay.
Other questions? Okay.
Let me ask a question.
Yeah.
With the new sky surveys that are coming up, and of course they don't dwell on a given part of the sky for a long period of time to get a light curve, but will you get help from the general mapping and astrometry? You know, once Vera Rubin goes into operation, for example, it's a very big telescope to do a sky survey.
Yeah. So I'm sorry, is your question, Ken, whether we'll get data from that for?
Yeah, will you get data? Will
Exoplanets?
that help the exoplanet search? I know it won't dwell. It would be nice if it would.
Yeah, I don't know, because I would think that with TESS and James Webb, I don't know what that the Rubin, for example, could contribute. Certainly, the Roman Space Telescope, being in space and being able to with its large telescope, be able to help with exoplanet atmospheric characterization. I'm not sure what Rubin will help with, quite frankly. Any other questions? Okay, well, thank you all very much for the time. And if anybody wants to reach out to me independently of this, I'll be happy to try to answer any other questions that might come to mind.
Well, thank you very much for being with us tonight and give us this great talk.
Sure, my pleasure.
And, you know, if you're ever in San Diego again, please look us all up, and
Okay,
we
will
can
do.
do some imaging and observing together.
Yeah, well, thank you. All right, thank you.
Well, if no one, any final questions, observations, remarks? I guess not. Well, again, thank you for the great talk, and let's conclude the meeting. See you next third Wednesday at Mission Trails, again with a Zoom presentation. We'll see how the hybrid in-person works. Again, I'm sorry, without any cookies. Take care.
Thank you.
Bye-bye.
Bye-bye.